Hey folks, Dr. Vivi here with another office hours chat, this time about minimizing formal charge. So this video is for you if you currently feel confident calculating formal charges for a given Lewis structure, but you aren't yet sure how to minimize formal charge or how to figure out if a Lewis structure that you think might be a good Lewis structure is in fact the optimal Lewis structure once we take formal charge into account. And so to tackle this topic, I'm going to give us an example of BrO3-, also known as the bromate ion. And so I've gone through and already calculated the total number of valence electrons and a structure that strictly obeys the octet rule on all the different atoms for this compound, which if you're following along with our lecture notes is steps 1 through 5 of how to draw a Lewis structure. What we have to tackle still, and what I'm going to show you in this video, is how we calculate, optimize, and then minimize the formal charges. So in terms of calculation, again, I'm going to go pretty fast since this video assumes that you already feel comfortable calculating formal charge, but we can see that this oxygen that's at the top currently has 7 valence electrons. According to the periodic table, oxygen should have 6 valence electrons, so that means that we're ending up with a formal charge of -1 for this top oxygen. The other oxygens look identical, and so we can see that both of these also have formal charges of -1. And that last but not least, for our bromine atom, we see that this currently has 5 valence electrons. It should have 7 valence electrons. And so that means that we end up with a formal charge of +2. And so hopefully, based on our rules that we discussed in class about formal charge, you might start to suspect that this might not be the optimal Lewis structure. And in fact, I think seeing multiple formal charges, particularly when you have some negative formal charge and some positive formal charge on neighboring atoms, is a really good clue that we don't yet have the optimal Lewis structure. And so what I want to show you right now is a tip for removing unnecessary formal charge and coming up with a more optimal structure. So my tip for us is going to be that we can minimize formal charge on 2 neighboring atoms by turning a lone pair into a double bond. And in particular, we want to take a lone pair from the atom that currently has negative formal charge and turn it into a bond with its neighboring atom that has the positive formal charge. So to convince you that this works and that this is going to make our structure look a little bit better, let me now show you what our bromate ion looks like when we had, instead of a single bond, treat it as a double bond between the bromine and the top oxygen. So the formal charges on my bottom 2 oxygen atoms are not going to change because we haven't changed anything about their environment. However, looking at our oxygen one more time, we now see that the top oxygen has no formal charge, and our bromine atom, which I should make sure to draw the lone pairs on, now only has a formal charge of +1. And so according to our rules for formal charge, this structure is looking a little bit better because it has fewer formal charges than the previous one. And so anytime you come into a situation where you notice formal charges, one positive and one negative, on neighboring atoms, you can use that tip that I showed in pink in order to help make sure that you minimize formal charge. However, we should still keep asking ourselves, is that the best we can do with this structure? And you may notice that we still have neighboring positive and negative formal charges showing up. So let's go ahead and repeat that same tip on one of the other oxygens. I'm going to take my lone pair and I'm going to turn it into a double bond. Remember, at this stage of drawing our Lewis structures, we are not allowed to eliminate or add in additional electrons, and so anything we do to change the structure simply needs to be rearranging the electrons. And if we go ahead and do that, now I'm going to have a bromate ion that has 2 double bonds between the bromines and the oxygens, and one of the oxygen-bromine bonds left over as a single bond. Recalculating our formal charges one last time, hopefully everyone can see that we still have a -1 formal charge on the oxygen that has a single bond with the bromine, but all of the other formal charges have been eliminated. And so hopefully you can see at this point that compared to our three different structures, the structure that I'm showing in the bottom left-hand corner is the best out of those three structures. And oftentimes I'll see students asking at this point, how do I know that here I'm at the best structure? And I would say that there's two different ways that you can know that. The first is that I don't see any adjacent positive and negative charge pairs. The second is that because this is a negatively charged species, remember that the sum of the formal charges has to add up to the overall charge on the atom. So since this is a bromate ion, not a neutral compound, there's no universe in which we're going to get a compound with 0 formal charges everywhere. So there has to be at least one formal charge somewhere. And because it's currently placed on the oxygen atom, which is relatively electronegative, I feel pretty confident about there being the negative formal charge there. And so in this case, it turns out this third structure that we drew is going to be the structure that is the correct answer that has the minimized formal charge. And so again, it was really that major tip about being able to know where to form multiple bonds in order to break up those formal charges on neighboring atoms that helped us know a little bit more systematically how to get to this answer. Let's go ahead and do one more example so that we can see a related tip in practice. So now we're going to go ahead and tackle the compound boron trichloride, which again, I've taken the liberty of calculating the total number of valence electrons and drawing a version of the Lewis structure where I've prioritized obeying the octet rule on all the atoms. Let's go ahead and calculate our formal charges one more time. The top chlorine currently has 6 valence electrons, but it really would like to have 7 valence electrons. So its formal charge in this case is going to be +1. The boron has 4 valence electrons, but the periodic table says that it would normally have 3. So this is going to have a formal charge of -1. And then meanwhile, the bottom two chlorines both have 7 valence electrons, and according to the periodic table, they should. So they don't have any formal charge. And so looking at this, I'm seeing once again that there is a positive-negative charge pairing. However, my previous tip was that you should take a lone pair that's on the more negative atom and turn it into a double bond. But unfortunately, with this boron, we don't have any lone pairs to work with on that atom. So a related tip is that you can also break double bonds. To change the formal charges. And so in this case, because I have too many electrons associated with the boron and not enough electrons associated with the chlorine, what I'm going to do is I'm going to take this double bond and I'm going to turn it into a lone pair that's on our chlorine. Redrawing our structure, this is going to give me a structure that looks like boron connected to 3 chlorines, all via single bonds. And if I go ahead and calculate my formal charges one more time, you'll see that there is in fact no formal charge on any of the atoms in this second version of the structure. And so the second version of the structure, we can say with a lot of confidence, is going to be the most optimal structure. So one last thing I want to point out before I end this video is that this gives a little bit more intuition to the fact where we expect to see exceptions to the octet rule. So last time in class, I got a lot of questions about, okay, I know bromine can have an expanded octet, but when will it have an expanded octet? And similarly, I know boron can have an expanded octet, but when do I know that it will have an expanded octet? And so the conclusion is that for the atoms that we discussed in class, namely boron, beryllium, and aluminum for the incomplete octets, and then any elements that are in period 3 and beyond for the expanded octets, that when they choose to have things that obey or that slightly disobey the octet rule, it's always so that they can minimize their formal charge. And so long as we pay a lot of attention to which compounds we need to modify the octet rule so that they can obey the more important rule of minimizing formal charge. That's going to help us clarify not only how to come up with an optimal structure, but also to know when we expect to see violations to the octet rule. I hope that helped us as a video, helps you understand a little bit better about how to minimize formal charge, and I'll look forward to seeing you all in class.